Hey everyone, this is the Quad Squad. We are made up of Bailey Petrie, Victoria Arno, Vincent View, and Jalen Nelson May. And this is our unknown hormone project for our pathophysiology class. Our code for this project is number 494. For this project, we are to identify an unknown hormone that was injected into a set of rats, 4 male and 4 female, based on 2 datasets. One of the datasets comes from rats that were injected with the unknown hormone, and the other comes from a control set of rats that were injected with saline. These datasets contain a range of items that have changed because of the injected unknown hormone. These 2 sets of rats were treated up to 10 days and were administered the unknown hormone anywhere from 1 to 4 times in those 10 days. To start, we were given a list of possible hormones that could have been injected into our experimental set of rats. This list includes TSH, which is known as the thyroid-stimulating hormone, and it stimulates the thyroid to produce other hormones such as T3 and T4, thyroxine, which is known as T4 and works to regulate the body's metabolism, glucocorticoids, which work to reduce inflammation and repress the immune system, ACTH, also known as adrenocorticotropic hormone, and is produced by the pituitary gland and initiates the production of cortisol. Growth hormone, which is produced by the pituitary gland as well and stimulates the growth in children and adults. HCG, also known as human chronogonadotropin, which is present in women that are pregnant. Testosterone, which is a male sex hormone. Estradiol, which is a female sex hormone. Epinephrine, which is known as adrenaline and is often seen in your fight and flight responses. A placebo, and somatostatin, which is produced in the hypothalamus and inhibits things such as growth hormone and TSH. To start our search for the unknown hormone injected into our rats, we compared the control and experimental datasets. We started first by finding the range of each item in our dataset. That way we could make graphs and determine what data is of significance and what data we could put to the side when starting our search. These upper and lower ranges can be seen at the side of each item. To find upper ranges, you take the mean and add the standard deviation. For the lower ranges, you take the mean and subtract the standard deviation. After this, we made graphs for each item, which is explained on the next slide. However, the yellow highlights on this slide on the experimental data set are the items that are of significance after looking at the graphs.
After getting the data for the experimental rats, we decided to create line graphs showing standard deviation so that we can see a visual comparison of the 2 data sets. These line graphs can show us which areas are of significant difference, meaning a hormone was affecting the area. We can also see which lines are of interest, meaning we should keep an eye on these areas because it's possible a hormone is affecting them. Finally, we can see if an area is of no interest, meaning the experimental rats data was close enough to the data of the controlled rats that we can say a hormone did not affect the area of interest, and we can eliminate hormones that directly correlate to said area. Taking a look at our data, we see that the total body weight gained by the rats was much less than the control, so weight gained is significantly different. Next, we see the weight of the thymus was also much lower, making it significantly different. The adrenals were also significantly different, seeing as their weight increased compared to the control. The thyroid weight was of no interest because the standard deviation of the control overlapped with the mean of the experimental group. We decided the thyroid activity was of interest in that it was more active in the experimental rats than the controlled. Tibia width of the experimental rats was much lower than that of the controlled, so we noted it as significantly different. The ovaries in the female experimental rats generally increased, and our group deemed them of interest. The standard deviation of the controlled rats' uteruses overlapped with the mean of the experimental rats, so the uterus is of no interest. The weight of the pituitary is of interest, and we noticed that generally the experimental rats decreased. In the male rats, the seminal vesicles had no change, so they are not of interest. Again, in the male rats, the prostate had little to no change in size, so they are of no interest. The testes are also of no interest because there is no change in size. Lastly, the experimental rat's blood fat was of significant interest because it increased greatly. This is the graph for the glucose tolerance test. The controlled rats are in gray and the experimental rats are in green. We see that the experimental rats experienced elevated but controlled blood glucose levels, which we consider of significant difference.
How we narrowed it down. We first ruled out somatostatin, this being because our rats had elevated blood glucose levels. Pancreatic somatostatin works to inhibit the secretion of insulin and glucagon. We then ruled out testosterone and estradiol because both hormones promote change in the sex organs. However, our rats had very little to no change seen in the testes, ovaries, vents, prostate, or seminal vesicles. We were then able to rule out HCG as it contributes to sex organ changes, and there were very little to no changes seen in our rats. We then ruled out placebo because it was of insignificance to the changes seen in our rats. Narrowing our hormones down even more. Continuing the elimination process, we ruled out both TSH and thyroxine, this being because the changes in the thyroid were of interest, but the changes were insignificant. Lastly, we ruled out GH because our rats were losing significant amounts of weight, therefore meaning a lack of GH was being produced. After narrowing down the hormones and eliminating the insignificant ones, our top three potential hormones were glucocorticoid, ACTH, and epinephrine. In our consultation, we discussed our elimination process and how we narrowed it down. We further discussed what our hormones could potentially be, and our final three hormones were validated.
Our group decided to request the rats' vital signs for our first test. The experimental rat's heart rate increased greatly and was of significant difference. The respiratory rate of the experimental rats increased a little, so we considered them of interest. The temperature of the experimental rats was significantly higher than that of the controlled rats. Finally, the systolic and diastolic blood pressure of the rats increased and were of significant difference. The mean blood pressure of the controlled rats was 170/100, while the mean blood pressure of the experimental rats was 207/121. It was also observed that the experimental rats had scraggly hair and their skin bruised easily.
For the glucocorticoids, it may cause thinning of skin, hirsutism, decreased weight, muscle and bone mass, increased blood pressure, body temperature, heart rate, respiratory rate, blood glucose level, and blood-free fatty acids. Our vital sign has confirmed that there was an increased heart rate, respiratory rate, temperature, blood pressure, bruising, and scraggliness of the hair. For ACTH, it may cause thinning of skin, increased hair growth, blood pressure, fat accumulation around neck and shoulders, body temperature, heart rate, respiratory rate, and blood pressure. It will also decrease the amount of plasma FFA. One thing to note about vital signs is that there was scraggly hair instead of increased hair growth. For epinephrine, it may cause hair loss, decreased weight gain, bone loss, increased blood pressure, body temperature, heart rate, respiratory rate, blood glucose level, and blood FFA. In our vital signs, there was bruising, in which epinephrine does not cause bruising. For our second and third tests, we did the radioimmunoassay for glucocorticoids in blood and urine vanilla mandelic acid test for epinephrine in urine. In our RIA, the experimental group possessed lower counts per minute in comparison to the control group. The low counts per minute in the experimental group would be indicative of elevated levels of glucocorticoids in blood. In our urine vanilla mandelic acid test, both the control and experimental group had the same results, which was a single plus sign. High levels of epinephrine would have been indicated by triple plus signs, meaning that there was no excess of epinephrine in the urine from an injection. These results would put glucocorticoids as more of a possibility for the unknown hormone.
Taking all three tests into consideration, our data suggests that most likely a glucocorticoid was the unknown hormone injected into the rats.